orbits of stars and gas and dust in a spiral galaxy are such that they produce spiral arms that are regions of enhanced density, but any given star goes around the galaxy, and sometimes it goes into a spiral arm, and sometimes it goes in between spiral arms. So sometimes the sun is in a spiral arm, sometimes the sun is not in a spiral arm, because the stars are moving around the galaxy at a different rate than the density waves are. And so this figure from your book is illustrating the idea. It turns out that the disk of a galaxy, you can show it's unstable to the production of these density waves. If you give it, how do I want to say this? If you perturb it, if you disturb it a little bit, it naturally tends to rearrange itself so that density waves form. And the idea is that the orbits of stars and gas and dust at different distances from the galaxy are kind of systematically tilted in different directions. The long axes of the orbits are systematically tilted along different directions. And as a result of that, imagine that there's 4 stars moving along here. Right now they're relatively far apart from one another, but as they continue around the galaxy, their orbits come together over here and they get closer together. And where the orbits get closer together because of this tilting effect is where the spiral arms are. And spiral arms are active sites of star formation because when you apply this idea to molecular clouds where stars can form going around the galaxy, they tend to pile up and bump into one another and compress one another in these pileups here and touch off star formation. And as a result, we see hot young blue stars along the spiral arms because of the fact that that's where interstellar clouds are bumping into one another and touching off star formation. So the analogy that Phil Platt made in the video that I showed is that spiral arms are kind of like traffic jams. In other words, on a road, if you're in a car and you get into a traffic jam, you slowly make your way to the front of the jam and then you're not in the jam anymore. And similarly, stars kind of are in traffic jams when they're in the spiral arms, but as they keep driving, so to speak, they move out of the spiral arms. And so sometimes the stars are in the regions where the spiral arms are, sometimes they are not. Any follow-ups on that? Okay, so now, would you like to ask her question? Yes.
Can you just go over bubbles, super bubbles?
Oh yeah, bubble. Right, you did ask it already.
Yeah,
Okay, so bubbles and super bubbles. Right, sounds like a commercial for gum or something. But okay, so bubbles and super bubbles. So I think I actually have. So I'll just bring it up. It's discussed in your book in chapter. I think it's. Is it? Do I have that under 20 or 19? 19. So it's discussed in your book under 19, but I actually waited until we were doing chapter 1 to talk about it. So I've got the slides here in chapter 21 about galaxy evolution, but that's okay. You can find these the original images, this image from your book in chapter 19. So I put a chapter 19 figure in my chapter 21 slides. So, when a supernova goes off, a massive star explodes, it sends material at very high speeds into the surrounding interstellar medium. It's moving faster than the speed of sound in the interstellar medium, and that high-speed hot material from the supernova kind of blows a bubble in the interstellar medium. It excavates a kind of bubble of hot, lower density gas in the interstellar medium surrounding the location where the star blew up. So that's a bubble. It's a cavity in the interstellar medium blown by the material that comes off of a supernova. And a star cluster has lots of massive stars that blow up as supernovae. So you get supernova after supernova after supernova their bubbles can merge together and create a much larger bubble in the interstellar medium, and so that's a superbubble. Overlapping bubbles from lots of supernovae produce a superbubble. A large star cluster would tend to produce such a thing. And if the superbubble of expanding hot material makes it all the way to the top of the galactic disk, then you can kind of spring a leak and you have material that squirts up above the disk like a fountain, so to speak. So it's much less dense than a water fountain is, but a water fountain, you've got water shooting up. So here we've got hot gas from supernovae in the superbubble shooting up above the disk of the galaxy. But it's going to cool down as it expands. And so eventually that hot material cools down and condenses into cooler clouds of gas, and so that's indicated with blue here, just because people think, well, of course, really, blue is hot in star colors, but blue is a cool color, so to speak, from our artistic standpoint. So they're doing this artistically and showing cool blue here is supposed to the blue here is supposed to represent cooler material that has cooled off at the edges of the fountain. And then the gravity of the disk will pull that material back down again. So you'll get a rain of cool gas back into the disk, which can then seed additional star formation. And so that's the galactic fountain model. That the idea that in fact star formation is probably episodic, because the blowing up a fountain like this is robbing the disk of material that could be forming stars. So for a while in that region, the star formation rate would go down, but then the material rains back down into the disk and collects, and you can form new stars again. That's the galactic fountain model. Yes?
This is awful.
Okay, so anybody want to follow up anything with that? Okay, take it away.
So are gravitational waves just resolve once you black holes?
So gravitational waves occur whenever mass moves around. So in other words, when I wave my hand, my waving hand is creating gravitational waves. However, those are of such tiny, tiny strength that we have no hope of detecting. We can theoretically predict that my waving hand is producing gravitational waves. I don't think we'll ever make a detector that could actually see them, so to speak. The point with merging neutron stars or black holes is now we're talking. In other words, now we have a huge amount of mass waving around when you've got two black holes merging into one another. And as they get close to one another, the gravity gets stronger and stronger. The curvature of space-time gets stronger and stronger. And just as if you had a rubber sheet and you went on the rubber sheet, you would make ripples spread away from the rubber sheet. Well, remember, gravity is curvature of space-time. So if you have masses doing this, they are making rapidly changing curvature of space-time that gets carried away as ripples, so to speak. Those ripples in the fabric of space, changing curvature that travels away at the speed of light, those are the gravitational waves. And if you have black holes merging, the gravitational waves are strong enough that with extremely sensitive detectors on Earth, we can detect the gravitational waves from black holes that merge billions of light years away. But only since 2015 has the technology finally matured to the point where we could do this. I've been reading about people trying to detect gravitational waves since I was a kid, and I was always like, well, maybe I'll live long enough to see it happen. And I did, I survived until 2015 and finally saw gravitational waves be detected. It's one of those things where if you were thinking about a career as an astrophysics researcher, you got to think, well, let's see. If I go into gravitational waves, I'll probably never see anything, but if I do, I'll get a Nobel Prize. It's kind of like that kind of situation. So it's high risk, high reward. And for many decades, the risk is what people fell prey to, that we just didn't have the technology for it. So people would spend careers trying to find gravitational waves and coming up empty. But it finally paid off. So. Yes?
This is the
Yeah, any follow-ups on the gravitational waves? Yeah,
Yeah, so just, the second part of that question about LIGO,
yeah.
do we need to know, like, the one in 2015, what they saw?
What did I say exactly? I don't even remember what I said exactly.
It says no gravitational waves are and what kinds of events cause the burst of gravitational waves detected by LIGO.
Yeah.
So just
So in other words, merging neutron stars, merging black holes, and neutron stars and black holes merging. Those are the things that we are seeing with LIGO. Neutron stars merging with other neutron stars, black holes merging with other black holes, and neutron stars and black holes merging with one another are the events where you got something massive enough, two things massive enough to shake things up enough to make LIGO detectable gravitational waves. Yeah.
So how did they know the one in 2015 wasn't just two neutron stars?
From the signature, in other words, from the detailed plot of the amplitude versus time of the waves, they were able to determine that it had to be black holes merging in order to do that. They look different depending on whether they're similar but different enough that you can tell what you're dealing with there. They were able to estimate the masses of the two objects, and they were, I forget what they said, but it was like 20 and 35 solar masses, and both of those, that's both way too big to be neutron stars. It's just too big. Yes?
How does the cosmological redshift differ from the Doppler shift?
Yeah, so a Doppler shift, remember, is due to the motion of an object through space. In other words, if a train is coming towards you, remember that because where each wave front is emitted is at a different location, then the waves pile up, the wave crests pile up in front of the source, stretch out behind it, and so you see a blue shift or something moving towards you and a red shift or something moving away from you. So a Doppler shift is due to motion of objects through space. On the other hand, the cosmological redshift isn't due to the motion of a galaxy through space relative to the Milky Way. It's due to the expansion of space while the light was on its way to us, between us and the distant galaxy. So as space expands, all the wave crests are moving at the speed of light through space, but the space between them is expanding because of the expansion of the universe. So the analogy I made in class was two cute little ants that are walking along at the same speed on the surface of a balloon. If the balloon isn't blowing up, they keep the same distance from one another. But if the balloon is being blown up at the same time, even though they're both crawling along the balloon at the same speed, they get further apart because the rubber between them is stretching. And similarly, as photons travel through the expanding universe, traveling millions or billions of light years from a distant galaxy, so that they take millions or billions of years to reach us, as space expands that whole time, the wave crests are being stretched apart from one another by the expansion of space. So the redshift we see from distant galaxies isn't because they're flying away from us through space, it's because the space between us and the galaxy has been expanding while the light was on its way to us. That's a cosmological redshift. Yes?
Question.
Is it a different question or related?
It's unrelated.
Unrelated. Okay, then wait a minute. Okay, did you want to follow up on that?
Okay, so what you're saying is with the redshift, the space between us and the galaxy is expanding?
It's expanding, right? Because remember, the universe is expanding.
Right, so because that space between us is expanding.
So as the light is traveling from us to the other galaxy, from the other galaxy to us, the whole time it's been traveling through expanding space, and that is stretching out the wavelengths. It's kind of like if you had a sheet of rubber and you made shades on the sheet of rubber. You took a marker and drew strips on the sheet of rubber to represent the crests of the light waves, where the electric field was strongest. If I took a rubber sheet and drew stripes on it like that, and I stretched the rubber sheet, the marker strips would get further apart from one another because of the stretching of the sheet. And it's very similar with photons traveling through the universe. They're moving, but the space between the wave crests is stretching as they travel, and so the wave crests get further apart because of the expansion of the universe. And because if we look at a distant galaxy, there's been enough time for substantial expansion of space during the time that the light was on its way to us, it can cause a noticeable shift in the wavelength of the light. The light's wavelength has been stretched by the expansion of space. That's a cosmological redshift. It is a redshift, an increase in wavelength caused by the expansion of space in the universe. Is this a follow-up to that too? Or, okay, wait a minute, then I'll get to you, but Teresa was about to ask you a question.
Can you highlight the Hubble redshift distance relation?
The Hubble redshift distance relation, yes. So that's this business, we did all those lecture tutorials on that, where we find that the farther away a galaxy is, the faster that it is moving away from us. But again, it's not because it is flying away from us through space. It's because the space between us and that galaxy is expanding. And so here's a Hubble plot where we've got recession velocity on the y-axis, distance to the galaxy on the x-axis, and if we don't go too far away in space, then we see that you get a nice straight line relationship. And so then the idea is that the speed of recession is h0 times the distance to the galaxy. That's the Hubble relation. You get a nice plot like this. The slope of the plot is the Hubble constant, h0. And it arises because if there's twice as much space between us and another galaxy, then there will be twice as much expansion of space. So the reason why a more distant galaxy is moving faster away from us is simply because there's more space between us and that galaxy that is busy expanding. And so therefore it's being carried away from us faster than a nearby galaxy is. And the classic analogy is coins on a rubber sheet, where you expand the rubber sheet uniformly in every direction. No matter which coin you're on to represent a galaxy, every other coin is getting further away from you. And the further away a coin is to begin with, the greater its change in distance from you in any given amount of time, because the more rubber is between you and that distant coin, the more rubber has stretched. Similarly in our universe, the more space is between us and the galaxy, the more space there has been stretching between us and that galaxy, and so it's being carried away from us faster than the expansion of space. That's the Hubble relation. Yeah, be sure to review those lecture tutorials we did about all that. Yes?
Can you explain the lighthouse model for pulsars?
Yeah, so the lighthouse model for pulsars is an explanation of why pulsars appear to flash on and off many times per second. And the analogy we make is with a lighthouse on Earth. So, you know, so you can see this with water towers that have spinning lights on top of them. So, you know, we don't have lighthouses around here. If you go to Lake Erie, you can see lighthouses. If you've ever seen a lighthouse, right, it goes blink, 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 right? Have you seen that before, like with a lighthouse? Now, is it that somebody is somebody's like turning a light on and off? No, it's that there is a beam of light which is being swept around, and every time the beam is pointing at you, you see a flash. And so the analogy is that a neutron star has beams of radiation coming out of its north and south magnetic poles. Two beams of radiation coming out of its north and south magnetic poles. And in general, the rotation axis and the north-south magnetic axis aren't aligned with one another. And so if I had like, well, I can't use my phone is recording this. But if I have like a flashlight to represent one of the beams from the pulsar, and I'm the neutron star, and I go like this, every time the beam is pointed towards Earth, years later, because it takes like years to get to us from the pulsar, years later we see a flash as a result every time the beam sweeps past Earth, and so we see flash, 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 flash because of the spinning beams that keep crossing in our direction. And that's the lighthouse model, because it's very similar to a lighthouse. Yes?
This is unrelated to that.
Unrelated. Anybody want to follow up on lighthouse? Okay, go for it.
Alright, what are standard candles?
Standard candles, the name is suggestive in the following way. If you had a manufacturer that very carefully controlled their candles, you know, the wick and the wax and all that kind of stuff, you could expect to have candles such that every candle from that manufacturer is giving off the same amount of light. And if you knew how much light that was, and you saw the candle some distance away, you could measure how bright the candle appeared to be, and you could use the inverse square law for light and how bright you knew the candle was to figure out how far away the candle was from us. And conveniently enough, nature has provided us with something analogous. There are various astronomical phenomena that we're able to know their brightness. We're able to know their true luminosity. The classic example is Cepheid variables, which have a distinctive relation between how long they take to go from brightest to dimmest back to brightest again. So in other words, their period, how long they take to go from their brightest back to their brightest again, and their average luminosity. And this is the period luminosity for Cepheid variables. So and the other thing is they're very bright to begin with. They're like more than 1,000 times the sun's luminosity, which means we can see them in other galaxies. They're so bright we can see these individual stars in other galaxies. And so if we are looking at a Cepheid variable in another galaxy, and we find that its period is 30 days. It goes from maximum brightness to minimum brightness to maximum brightness regularly every 30 days. Well, based on measurements of more nearby Cepheids, we can say, okay, that Cepheid with a period of 30 days is about 10,000 times the sun's luminosity. I know how bright it really is. In this galaxy, it looks this bright. I measure how bright it appears from Earth. I say it's really 10,000 times the sun's luminosity. Based on the inverse square law, I can calculate the distance to that galaxy. And that's how Hubble was able to show that the Andromeda Galaxy is simply too far away to be something within our own Milky Way galaxy. He found a Cepheid variable, this particular one in fact, within the Andromeda Galaxy, measured its brightness variations, calculated how luminous it was from the period luminosity relation, determined how far away it was based on that, and it was way too far away to be part of our galaxy. So that's how he got the clinching proof that spiral galaxies like the Andromeda Galaxy are separate cities of stars, so to speak, from our own. Yes?
Is the emitting of X-ray rays from accretion disk around neutron stars, does the same thing go for if an accretion disk is surrounding a black hole?
It does. So both neutron star and black hole accretion disks, the gravity is strong enough in both of them that the material towards the center is going around really fast, heated to millions of Kelvin, hot enough to give off X-rays. So seeing X-rays by itself doesn't tell us whether it's a neutron star or a black hole that the accretion disk is around. We have to have some way of estimating the mass of the object that the accretion disk is around. And if that is too massive to be a neutron star, we infer that it's a black hole. Accretion disks around white dwarfs don't give off X-rays because the gravity isn't as strong, the gas doesn't orbit as fast, so it doesn't get hot enough to give off X-rays. But if neutron stars, black holes, yes, hot enough to give off X-rays. Yes?
So I'm sorry,
they give off X-rays because they're hot enough and they're rotating fast enough?
Yeah, but those are not uncorrelated. In other words, the reason that they're hot is because, remember that Kepler's third law says that the closer the material is to the center, the faster it's moving. So material closer to the neutron star or black hole in the accretion disk is literally moving faster than material further out. Well, here's a case where one of my hands is moving at a different speed than my other hand, right? And you know that if you do this, friction heats up your hand. So the idea is that everywhere in the accretion disk, the further away, the closer you get to the center, the faster the material is moving. So layers closer to the center are rubbing against layers farther from the center because they're moving faster. And that friction heats the disk. And in an accretion disk around a black hole or a neutron star, the material is going so fast that the friction heats the disk to millions of Kelvin, hot enough to give off X-rays. Yes?
Could you explain our galaxy's formation in terms of the collapse of a protogalactic cloud?
Yeah, so we know that protostars form from protostellar clouds. And remember that the story is that when the sun, for example, formed, it started as a large cloud of gas, mostly hydrogen and helium with some dust mixed in. And a tipping point was reached, probably because of a passing supernova shockwave that compressed it a bit. Gravity became stronger than pressure, and it started to collapse under its own weight. And as it collapsed, its moment of inertia got smaller, and angular momentum conservation meant that it started to spin and flatten out. And so, as a result, the sun formed a protostellar disk around it. Most of the material fell into the proto-sun, and there was a flat rotating disk around it because of angular momentum conservation, making it spin faster as it collapsed. And then the planets formed in that disk, which is why the solar system has the sun and a bunch of planets that are all orbiting in essentially the same plane. That was the plane of the protostellar disk. So by analogy, the idea is with a protogalactic cloud that we have a bigger version of that. We have a galaxy-sized version of that happening. And so the idea is that you start with now something that's bigger than a galaxy collapsing. And as it collapses, if it has significant angular momentum, it starts to spin, and that makes it flatten out into a disk. And so the basic idea then is just like a star has a protostellar disk around it, when it forms a collapsing protogalactic cloud spinning faster and faster, can produce a disk galaxy as a result. And that's the basic model there of the galaxy forming from the collapse of a protogalactic cloud. It's like a bigger version of a protostellar cloud. But further studies and observations of very distant galaxies indicate that probably this happened, but at the same time, multiple smaller protogalactic clouds that formed small galaxies initially, protogalaxies initially, merged with one another, so that our galaxy was actually ultimately the result when it was forming of mergers of multiple smaller protogalaxies, rather than a single giant protogalactic cloud collapsing all at once to form our galaxy. She wins, but I'll get you after her. Yes.
Simple question, and
Yeah.
I feel like it's also probably just intuitive, but just want to double check. What is a nova and what causes it?
That's not an intuitive question at all.
Okay.
No.
Awesome.
That's totally not a simple question.
Awesome.
Right. So we actually didn't really talk about it in class. It's in the book. Okay. So you didn't miss anything in class about this. So remember that a white dwarf supernova can form because of a white dwarf that's in a binary star system. It has a companion star close enough to it that it loses mass into an accretion disk surrounding the white dwarf. Now, if enough mass accumulates on the white dwarf, it can blow up as a white dwarf supernova. But before that happens, it can undergo a series of smaller explosions that are the nova explosions. The idea is when enough hydrogen from the accretion disk collects onto the surface of a white dwarf, it keeps getting compressed and compressed and compressed, and when it reaches 10 million Kelvin, that's enough to start hydrogen fusion. And because it's degenerate, it's sitting on a degenerate white dwarf surface, it goes out of control. And so what a nova is a temporary thermonuclear explosion on the surface of a white dwarf that has accumulated hydrogen from an accretion disk donated to it by a companion star. And it's spectacular, but it's not as spectacular as a white dwarf supernova. A white dwarf supernova becomes like a billion, a one with 9 zeros after it, times brighter than the sun. A nova outburst is only about 100,000 times brighter than the sun, only temporarily. So I've seen one nova in my life through binoculars. I've seen a nova. So that was cool. You know, it's like, oh wow, that's a nova. Because back when I was a kid and we didn't have the internet the way we do. The internet was proto-existing, but not the way it is today. There was a nova in Cygnus, Nova Cygni, that became bright enough to be seen with the naked eye, and I'm still mad that nobody ever told me about it, but that's okay. I've seen other great things. And maybe I'll see Betelgeuse blow up.
Yeah.
That's what I'm
You still
counting
got
on.
that going.
That's right, blow up. Yes.
So you say that so the white dwarf undergoes multiple explosions.
Yeah, so typically what would happen is that you would undergo multiple nova explosions. Now, the thing is, they're frequent on an astronomical time scale, but on a human time scale, they're at least thousands of years apart. So in other words, we humans are not going to see any one star go nova, 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 or anything like that. But typically, if you have a white dwarf supernova, that white dwarf probably had multiple nova explosions before it went white dwarf. The nova blasts off a lot of the material, the nova explosion blasts off a lot of material that accumulated on the white dwarf, but not all of it. So the white dwarf keeps overall gaining mass. And so you can have nova, 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 but then it gets massive enough that carbon fusion starts within the white dwarf and blows it to shreds. So it's kind of like boom, 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 boom! Because the supernova is way stronger than any of the nova explosions was. And really, I didn't, that last boom should have been like 10,000 times stronger than the other ones, but I didn't want to vaporize you guys, so I didn't do that.
How do the halo population of stars and disk population of stars differ from one another?
I had said that earlier. Were you here the whole time?
Yeah.
You might have zoned out. Yeah, it's fine. It's fine. It's fine. No, but I can quickly remind you. Okay, is that the disk population contains stars of all ages, and I may have neglected to mention this last time, but it's implicit in what I said. Stars of all ages and richer in heavy elements, because star formation has been occurring in a constantly enriching with heavy elements interstellar medium within the disk over billions of years. But in the halo, star formation started and ended billions of years ago. It started early in the history of the galaxy, it ended early in the history of the galaxy. So stars are no longer forming in the halo, which means they're all very old, and they are low in heavy elements. They don't have nearly as much in the way of heavy elements as disk stars do, because the interstellar medium didn't get enriched like the disk stars, like the disk interstellar medium did when the halo stars were forming. So much older and much less rich in heavy elements are the halo stars. Yes?
The halo,
doesn't really have an interstellar medium, right?
Correct, there's no interstellar medium there, right, which is why there's no active star formation there. There's nothing there to form new stars out of.
Okay.
Yeah, all the fun's in the disk. Actually, I shouldn't say that. If you were in the center of a globular cluster in the halo, a globular cluster can have like 1 million stars, and in the central regions, instead of the stars being light years apart, they're light weeks apart. So if you were in the center of a globular cluster, the entire sky would be filled with thousands of stars that are all brighter than the planet Venus is in our sky. It would be spectacular to see. Yes?
So there's a question that says, to be familiar with blue cloud and red
Yeah.
sequence that
Mhm.
appear when we plot galaxy luminosity versus
Yep.
color.
Mm-hmm.
I
Yeah, remind me, which chapter is that under?
20.
20, okay. Let's see. Okay, I think I didn't put,
I wasn't sure if that related to the,
yeah, let me just, I've got all the images from the text, in my drive, so let me just, find that image so that I can talk about it. But the blue cloud and the red sequence are what you get when you make kind of an HR diagram for galaxies instead of an HR diagram for stars. So, chapter 20, you said? Okay, so this is Cosmic Perspective, chapter 20. And so, let's see, will this let me, no, it's not. I wanted to show me little images, right, so that I'll know what I'm clicking on. Okay, here it is. This is the relevant image. So, with an HR diagram for stars, one way to do it is to plot color on the x-axis and luminosity of the star on the y-axis, because color is related to surface temperature. So we do the same thing with galaxies. For whole galaxies, we plot color. And you would do that by measuring how bright the galaxy is through a blue filter versus a green filter, it turns out. You can measure how bright it is through those two filters, and that gives you an indication of if the galaxy is blue in color versus red in color versus somewhere in between. Now, the color of a galaxy, for a star, its color depends on its temperature. A galaxy is billions of stars, so there's no such thing as the temperature of the stars in the galaxy. But on the other hand, if the galaxy has lots and lots of hot O and B stars in it, like a spiral galaxy does, it will tend to look blue. If a galaxy is an elliptical galaxy, its brightest stars are old red giants, it will tend to look red. So color is bluer for spiral galaxies and redder for elliptical galaxies. And then there's luminosity, and we find that there's a so-called blue cloud and a red sequence, two concentrations of galaxies in this diagram. And the blue cloud is composed essentially of spiral galaxies with active star formation, and the red sequence is elliptical galaxies that don't have it. And the brightest elliptical galaxies are much more massive than spiral galaxies are, probably because they form from mergers of multiple spiral galaxies. And so we think these guys up here in the red sequence are giant elliptical galaxies that probably form